Welcome to AI Paper Slop, where we summarize the latest AI and tech papers. Today, we're looking at Harness G, a graph-structured harness for search agents. And the core insight you need to know right now is that current RL search agents fail because of retrieval-equivalence collapse.
Right.
Basically, the model generates varying natural language queries that fetch the exact same documents, which destroys the contrast needed for optimization. So Harness G fixes this by replacing those free-form queries with a finite action menu over a paragraph sentence entity graph.
Mm-hmm.
And it introduces Structured Non-myopic Credit, or SNC, to perfectly assign rewards to both immediate and delayed bridge actions. The result, it crushes baselines like GraphR1 by over 10 points at the 1.5 billion scale on QA benchmarks.
Yeah, and for any ML engineers or, researchers tuning in, this fundamentally rethinks the policy environment interface for our edge agents. I mean, the community has spent the last year obsessing over tweaking reward functions.
Oh, absolutely.
Or, densifying credit signals just to make agents smarter. But this paper argues that the problem isn't actually the reward function.
It's not.
No, the problem is the interface itself. Like, the way the model actually talks to the search environment is structurally broken for reinforcement learning.
Right. So if you were building agentic systems right now, you really need to look at how your architecture might be failing under the hood.
Mm-hmm.
Because honestly, the narrative in this deep dive completely flips the conventional wisdom.
It really does.
To understand why we even need this graph-structured harness, we should probably look at exactly how current state-of-the-art models like Search R1 are completely breaking down.
Yeah, specifically during GRPO, so Group Relative Policy Optimization.
Right. The authors highlight this phenomenon they call retrieval-aliasing.
Yeah, so think about how large language models natively operate, right?
Yeah.
Their entire architecture is built to express intent through free-form natural language. So during that reinforcement learning training loop, you ask the model a question. It generates a query, like director of metamorphosis.
Okay, sure.
But in another rollout for that exact same prompt, it might generate Kafka metamorphosis director.
Right, which are technically different.
Exactly. On the surface, if you are just counting tokens, those are distinct strings. The model is exhibiting high query form diversity.
But, and this is the kicker, those distinct strings are getting embedded, sent to a vector database, and they just fetch the exact same top K chunks of text from the retriever.
Yep. The retrieval outcome diversity completely collapses.
Wow.
The paper actually tracked rollout groups spanning multiple equivalence classes. And at the start of training, the diversity is healthy. It's around 86%.
Okay, that sounds good.
But by training step 30, it plummets to below 10%.
Jeez.
Yeah, the policy is wildly varying its text queries, spending all this compute generating different tokens without ever reaching genuinely different retrieval outcomes.
That is wild. It's kind of like going to a restaurant and ordering a burger 50 different ways.
Exactly.
You say, I'd like a hamburger, and then the next time you say, I desire a beef patty on a bun, and then give me your finest ground chuck sandwich.
Right, yeah.
You're exerting all this cognitive effort to be creative, but the kitchen just sends you the exact same meal every single time.
You never actually learn what the tacos taste like.
Exactly. And this creates what the paper calls illusory exploration. I mean, the model thinks it's exploring the state space, but it really isn't.
Which creates an absolute nightmare for GRPO.
Right, because of how GRPO measures success.
Yeah, if you're familiar with how GRPO works, you know it relies heavily on contrasting different trajectories. It looks at a group of rollouts for the same input, calculates a baseline, and asks, well, which of these specific actions led to a better return?
But if all the trajectories gather highly overlapping evidence, they just reach utility equivalence. They all end up with the same information.
Exactly. If they all retrieve the same evidence and get the same right answer, their within-group advantages just vanish. The gradient dies.
Because the nominally distinct rollouts are providing zero new samples to learn from.
Right. Or worse, if they retrieve the same evidence, but somehow one rollout guesses the final answer correctly while the others fail, it completely confounds the retrieval credit.
Oh, because the success was just due to the downstream answer generator getting lucky.
Yes, not the retrieval action. But the system doesn't know that.
So it ends up updating the weights based on pure noise.
Exactly, pure noise. You just cannot reliably identify a better retrieval choice if the underlying evidence provided to the model is identical across the board.
Wait, hold on though. If the problem is the infinite action space of natural language, isn't the standard ML fix just to use process rewards?
You would think so, yeah.
Like, look, if you have this continuous text bottleneck, Why not just use a process reward model, a PRM, and grade the model's reasoning step by step for information gain? Why go through the massive engineering trouble of redesigning the whole interface?
Well, that is the exact logical leap that prior methods, like IGPO or step search, made. They tried densifying the reward using intermediate supervision.
Okay, but it didn't work.
They failed to fix the root cause. Because densifying the reward on a broken interface doesn't solve the underlying math. You still have that many-to-one mapping from strings to retrieval outcomes. If you reward the model for finding the right document using a PRM, but it can still reach that document using 50 different strings, you haven't restored effective contrast at the action level.
You're just giving it a faster reward for the same illusory exploration.
Exactly.
Okay. So you have to actually fix the menu you are ordering from, not just change how you tip the waiter.
That's a great way to put it.
If the action space is the problem, you change the action space. And that is exactly what the authors did with the Harness G interface.
Yep.
They threw out the infinite string generation entirely and moved the agent to a finite deterministic menu based on what they call a tripartite graph.
And the construction of this tripartite graph is brilliant, largely because of how practical it is for real-world engineering.
Okay, how so?
Well, it's built entirely offline, in near linear time, and crucially without using generative LLMs.
Wait, no LLMs at all. It's just paragraph nodes, sentence nodes, and entity nodes.
Exactly.
Let's break down how that actually works under the hood. Like, if I have a massive Wikipedia dump, how is this graph getting built without spending thousands of dollars on GPT-4 API calls?
Right, so you start by chunking the text into paragraph nodes.
Okay, standard chunking.
Then you split those into sentence nodes, which act as your minimal units of evidence, the actual facts the model needs to read.
Got it.
And to connect them, you just run standard named entity recognition tools. The paper uses Spacey, which is incredibly fast and cheap.
Oh, wow, Spacey. Old school, but effective.
Yeah. Spacey identifies entities, so people, places, concepts. These become your entity nodes. Then you use standard dense encoders to create semantic links. The entity nodes basically act as the bridging hops across different sentences and documents.
So instead of the model hallucinating a search query and just hoping the vector database finds something relevant, the policy just chooses an action ID from a finite menu based on this graph.
Exactly. The agent is restricted to 3 types of moves.
Okay, what are they?
First is select, where it commits a specific visible sentence to its internal evidence board. Second is lookup, which tells the environment to retrieve missing information around a specific entity it just saw.
And the third?
And third is answer, which just terminates the retrieval phase so the model can generate its final response.
And the environment executes this deterministically.
Deterministically, yes.
And it handles all the duplicate filtering for you. The paper highlights 3 properties of this interface that make it work: finiteness, verifiability, and previewability.
Right.
Finiteness just means the menu is strictly bounded. But verifiability is genuinely cool. I mean, if you are building an agent, you know how often models try to take invalid actions?
Oh, constantly.
But in Harness G, invalid actions, like trying to do a lookup on a date or a random adjective, they're filtered out before the menu is even rendered to the LLM.
Right. It prevents the model from wasting compute on dead ends. The bad move is just removed from the board entirely.
Which saves so much time.
But previewability is the property that truly unlocks the reinforcement learning breakthroughs we're going to discuss next.
Oh, because the actions are discrete index operations rather than generative text.
Exactly. The environment can simulate them in a read-only mode to see exactly what would happen without actually mutating the agent's state.
Okay, I have to challenge the core philosophy of this design, though.
Sure.
If you take away free-form queries, aren't you just lobotomizing the LLM's natural language reasoning capabilities?
I mean, I can see why you'd think that.
It sounds a lot like a regression to, 2018-era rigid knowledge graphs, where we forced models to walk down predefined semantic triplets. We're basically taking away the model's ability to talk its way through a complex problem.
Yeah, that is the totally natural reaction when you first read the premise, but the nuance here is critical.
Okay.
This is an open document graph, not a rigid knowledge graph with curated relations like X is the CEO of Y.
I see.
The LLM is still reading the raw, messy text of sentences. It still has to use its parametric knowledge to understand the semantics of what it's reading.
Right.
The difference is that it now makes exactly one semantic decision per step, like what specific piece of evidence should I commit to, or what entity should I pursue next.
So it's preserving the retrieval outcome diversity, but making the exploration highly interaction efficient.
Exactly. Every choice it makes on that menu is mutually exclusive by design.
Which focuses the reasoning instead of dumbing it down.
Yes. And because the actions are previewable, it allows us to completely rethink credit assignment.
Right. Which brings us to Structured Non-myopic Credit, or SNC.
Yeah, SNC. In traditional RL, figuring out if a specific action was good or bad is computationally exhausting. You usually have to roll out the trajectory to the very end multiple times just to compare outcomes and assign a reward.
Which obviously eats up massive amounts of cloud compute.
Huge amounts.
Okay.
But with SNC, they figured out how to mathematically calculate the exact value of an action compared to its alternatives without forcing the agent to do a bunch of extra rollouts.
Wait, how do they do that without rollouts?
They achieve this using a frozen answer score.
Okay.
At any given step, the system uses that previewability function to look at the immediate information gain of the chosen action.
Right.
But it goes a step further. It compares that gain against the mean gain of all the unchosen alternative at that exact same state. They call the unchosen alternatives the frontier.
This is the frontier relative advantage.
Exactly.
So let's say the model is at a specific state and has 10 valid lookup actions available. The environment quickly simulates all 10 using the frozen scorer. Yeah. If the action the model actually chose gets a score of, say, 0.8, and the average score of the other 9 options was 0.5, the advantage is positive 0.3.
You only get a positive reward if the action you picked actually outperformed the other feasible alternatives available to you right then and there.
Oh, that's incredibly elegant.
It eliminates the noise of superficial choices. You don't get heavily rewarded just for picking something that happens to contain the answer if 5 other obvious choices on the board also contain the answer.
That solves the local credit problem beautifully. But in complex multi-hop reasoning, the immediate information gain is often 0.
Right.
This is the classic delayed payoff problem, which SNC solves using structured enablement credit.
Yeah, let's walk through how this works in practice, because this is where the system gets truly non-myopic.
Okay, let's hear it.
Say you ask the agent for the birthday of the director of an obscure indie film. In step 1, the agent does a lookup on the film and finds a sentence saying the director is Caroline Leaf.
Okay, so Caroline Leaf is your bridge entity.
Exactly. But at that exact moment, the agent has not found the birth date. The immediate information gain for that action is technically 0.
Under normal myopic reward systems that are just greedy and only look at immediate payoff, the model gets penalized or ignored for this step.
Right.
It's exactly like an assist in basketball. I mean, the player who passes the ball doesn't score the points, but they made the play happen.
That's a perfect analogy.
If you only reward the player who shoots, nobody ever passes the ball. The system has to reward the assist. But technically speaking, how does the system actually track that?
Wow.
Like in a long chain of reasoning across thousands of tokens, how does it know which specific past action deserves the assist, rather than just blindly rewarding all early steps using some generic decay function?
This is where the strict bookkeeping of the Harness-G interface pays off massively.
Because of the deterministic environment.
Exactly. Because the environment executes everything deterministically, it creates a provenance-directed acyclic graph, or DAG, during the rollout.
Okay, a provenance DAG.
It strictly tracks provenance edges. It knows with mathematical certainty that action A produced the exact entity that was consumed by action C.
So when the agent finally does a lookup on Caroline Leaf in step 3 and finds her birth date, getting a huge spike in information gain, the environment looks at the DAG, traces the edge back, sees that step 1 provided the Caroline Leaf entity, and propagates that reward directly backward along that specific path.
Boom. It completely bypasses the noise of generic step-based decay. Downstream gains flow back through entire enabling chains.
Wow, that's smart.
It explicitly teaches the model the non-myopic pattern. First, find the bridge entity, then look up its missing attribute.
Right.
And because this is all based on deterministic environment bookkeeping and the frozen scorer, it requires 0 extra LLM rollouts from the policy model.
Okay, the theory is incredibly elegant, but elegance doesn't pay cloud compute bills.
Fair enough.
If you're an ML engineer sitting there wondering if you should implement this, your first question is going to be about empirical results and overhead.
Right. Does this actually scale?
Exactly. And they tested Harness G across 6 standard RAG datasets. For multi-hop reasoning, they used 2 Wiki multi-hop QA, HotPet QA, and Music.
Classic benchmarks.
And for single hop, they used natural questions, Pop QA, and Trivia QA.
And they used the Quen 2.5 Instruct backbone, which is a very solid baseline model for these kinds of tasks.
Definitely.
Harness G achieved the highest average F1 score at both evaluated model scales, so that's the 1.5 billion and 3 billion parameter models.
Okay.
And the margins are significant. It outperformed the strongest baseline, Graph R1, by 10.74 points at the 1.5B scale and by 3.98 points at the 3B scale.
Over 10 points on a 1.5 billion parameter model is massive. I mean, it really highlights how much latent reasoning capability is locked up inside these smaller models, just waiting for a better interface to unleash it.
Absolutely.
But what about the training overhead? Because you mentioned SNC doesn't need extra rollouts.
Right, and that is the critical point for anyone looking to scale this in production. Alternative methods like tree GRPO require extensive tree expansion rollouts to calculate step contrast.
Which means the model has to actually generate multiple paths forward to see what happens.
Which explodes your compute budget.
Yeah.
But SNC adds only 9 to 11% per step wall clock time overhead.
9 to 11% is negligible for the performance bump you're getting.
Completely negligible.
And it achieves that because all the frontier scoring and DAG propagation happens using read-only index queries against the frozen scorer. It's not doing full LLM text generations to calculate the reward.
Exactly. And the construction efficiency is just as stark.
Oh, right. Building the graph itself.
Yeah, we talked earlier about how the tripartite graph is built programmatically using spacey, sentence splitting, and dense encoding.
Right.
Because it relies on those traditional NLP tools, it costs exactly $0 in API calls to construct the graph over your corpus.
Which is a huge contrast to the current trend. I mean, the paper compares this directly to LLM-extracted graphs like Microsoft's GraphRag or HipperRag.
Right.
If you've tried building those, you know they can cost between $2.81 and $4.14 per query just to construct the knowledge structure.
Because you're running a heavy LLM over every text file to extract relationships.
Exactly. But Harness G gives you better performance on a smaller model without paying an LLM API tax just to organize your own documents.
Right. And if you are deploying agentic systems over massive dynamic open document corpora like a company's internal wiki or a live newsfeed, you simply cannot afford to run GPT-4 over every new text file just to update the relational edges.
You go bankrupt.
Exactly. The near-linear offline construction of Harness G makes it highly practical.
There is one specific paradox in the benchmark section that I found fascinating, though.
Oh, what's that?
The paper notes that late in the training process, Harness G actually uses more interaction turns than Search R1.
Okay.
It averages about 3.6 turns compared to 2.3. But despite taking more turns, it generates significantly fewer response side tokens.
Oh, wait.
Around 2.5K tokens compared to 4.3K.
Yeah, it's learning to navigate surgically.
Exactly.
Under the standard free query interface, the model tends to panic and ramble.
It really does.
It generates long, complex query strings, pulls in massive, noisy chunks of text from the vector database, and then it tries to reason over all of it at once in its context window.
Right, so it takes fewer discrete turns, but it's absolutely drowning in context tokens. It's a total garbage in, garbage out situation. If you ask a question and pull in 5 entire Wikipedia articles, the model has to burn compute just ignoring the irrelevant parts.
Right. But with the Harness G menu, the model makes quick, precise, discrete choices. It pulls in exactly the minimal evidence sentence it needs. It commits it to the board. It grabs the specific bridge entity. It executes one more lookup, gets the fact, and answers.
So it takes more discrete steps, but the total cognitive load drops significantly.
Yes, it's a much more efficient use of the transformer's context window.
So in our deep dive into this paper today, the grand takeaway is pretty clear. Harness G proves that fixing reinforcement learning for search agents isn't just about designing cleverer reward functions.
Right, or adding more fine-grained process supervision.
It's about fundamentally redesigning the action space the agent operates in.
Yep. By moving from infinite string generation to a deterministic graph-structured menu, we cure retrieval-equivalence collapse.
We make actions verifiable and previewable.
And we unlock mathematically precise credit assignment through SNC.
Which leads to a really provocative thought for you to take away today. I mean, for the last 2 years, the dogma in AI has been that natural language is the ultimate universal interface.
Totally.
But if capping an LLM's open-ended generation into a rigid, finite action menu actually increases its reasoning performance on complex, multi-hop tasks.
Maybe we've been overly obsessed with making models better at talking to
It's a
environments.
fascinating paradigm shift, really.
Yeah, maybe we should be designing environments that are better at listening to models through structured constraints.
Exactly. Will the future of agentic AI look less like conversational chatbots freely using tools, and more like LLMs serving as the reasoning engines driving highly structured, deterministic state machines?
It's a big question.
It really makes you wonder if our pursuit of purely natural language interfaces is actually the bottleneck holding back agentic reasoning. Something to think about as you build your next agent. We'll see you next time on AI Paper Swap.